Welcome everybody. Good morning and good evening. Good afternoon. So this is the final day of this year's summer school, and Alberto is gonna talk on his final lecture.
Okay, thank you very much. So as it was included in the plan, today I'm going to talk about the Laplacian flow for closed GTSS structures and its solitons. But before doing that, let me just make a small remark about something I said yesterday at the very end of the lecture, and regarding this example here by Fernandez, Fino, Kovalev, and Munoz. As I told you, this is a compact example admitting closed GTSS structures, but no torsion-free GTSS structures, whose first Betti number is equal to 1. And so far in the literature, all known compact examples of manifolds admitting closed GTSS structures, but no torsion-free GTSS structures, have first Betti number that is greater than or equal to 1. So this is the minimum possible Betti number that known examples admit. And let me know that yesterday I told you that there is an open problem regarding the existence of compact examples that are simply connected and admit closed GTSS structures, but you also have to add the requirement that that manifold does not admit any torsion-free GTSS structure. So the problem is whether there exists a compact 7-dimensional manifold that is simply connected, admits closed GTSS structures, but does not admit any torsion-free GTSS structure. So that's just a small remark about what I said yesterday. So today we can start with the last topic I would like to talk about in this mini course. And this topic is the Laplacian flow for closed GTSS structures and its solitons. So some special type of closed GTSS structures giving rise to special solutions. And you will notice some similarities between all the discussion on solitons and maybe what you saw last week when you attended the lectures on Ricci solitons for the Ricci flow. So which is the idea here? So as I told you in the previous lectures, so far we only have one theorem ensuring the existence of torsion-free GTSS structures on compact 7-dimensional manifolds, which is Joyce's theorem, and requires the existence of a closed GTSS structure with suitably small torsion on the manifold. So of course, one problem is to look for some new results ensuring the existence of torsion-free GTSS structures on compact 7-dimensional manifolds. And one possible way to tackle this problem is to use a geometric flow approach. So the idea of a geometric flow is to start with some geometric structure, for instance, a GTSS structure that you have on a 7-dimensional manifold of mixed GTSS structures, and evolve it by means of some evolution equation in order to obtain a solution of that evolution equation that, as far as it exists and as far as the time goes on, it improves its properties and eventually becomes torsion-free in the case of GTSS structures. So the problem in general is the following. So we would like to investigate the existence of torsion-free GTSS structures on a compact 7 manifold using a suitable geometric flow. And let me say that nowadays we have various proposals of geometric flows for G2 structures that aim at achieving this result here. But of course, this is a mini course on closed G2 structures. So we will focus here on the so-called Laplacian flow for closed G2 structures that was introduced by Bryant, and whose study in recent years gave a lot of results in this setting. So let's focus on this flow introduced by Bryant. You can find some information on the history of this flow and on the first properties in the paper by Bryant that you can find in the references. So this is the 2005 paper, some remarks on G2 structures. So he introduced a geometric flow for closed G2 structures. And the idea is the following. So let us assume that phi is a closed G2 structure on a given compact 7-dimensional manifold M. And let us consider a one-parameter family of G2 structures that will depend on a parameter that I shall denote by T. And let us assume that this family of G2 structures evolves as follows. So the time derivative of this free-form T, for the moment we put it equal to the differential of the codifferential of phi t, where recall that the codifferential in general is a map going from K forms on the manifold to K-1 forms, and it is defined by means of the Hodge dual as -1 to the following power. So we have the dimension of the manifold times the degree of the form +1, and again +1, times the Hodge dual, the differential, and again the Hodge dual. So this is a differential operator, and in the case where n is equal to 7 and the degree is equal to 3, as in the case we are considering here, then we have that this operator is just minus star d star. Okay, and this is the formal adjoint of the differential d. So in particular, in this case, so in this equation here, we assume phi t to be a family of G2 structures, and so this Hodge dual will be the Hodge dual induced by the metric induced by phi t. And now observe that if this reform phi t evolves in this way, and it starts at time 0 from this closed G2 structure we considered, then the closure of phi is preserved along this flow. So the closure of the initial datum, so let's say assume that at time 0 we have precisely this closed G2 structure we have fixed, is preserved by the flow equation. In fact, if you take the time derivative, let me denote it with the shortening of the differential of phi t, then clearly the time derivative commutes with the differential. So here you have the differential of the time derivative of phi t, but by definition this is equal to d star of phi, and so here you get 0. In particular, if the starting G2 structure is closed, then it stays closed along the flow. And so this allows you to rewrite the flow equation as follows. You have this operator we already had, and you can write it plus d star t of d of phi t in such a way that, since phi t is closed, so here we're just adding 0, but in such a way that here it appears the Hodge Laplacian induced by the metric G induced by phi t. And sometimes, as a notation, just to see shortening it, I shall write it as Laplacian determined by phi t of phi t. This is the Hodge Laplacian. Which is a second order differential operator. So in particular, you get the formulation of the Laplacian flow in the general case as follows. So let phi be a closed G2 structure on M compact 7 manifold. Then the Laplacian flow starting at phi is the second order geometric flow defined as follows. So we require the evolution of a 1-parameter family of G2 structures to be in the direction of its Hodge Laplacian. We require the tree form phi defining the G2 structure to stay closed along the flow. And we require that this family of G2 structures at time 0 is equal to the closed G2 structure we have fixed. So which is the idea behind this flow now? Is that if this flow is well posed on a compact manifold, which means that it has short-time existence and uniqueness of the solution for this problem, and if the solution exists for all real times, then the expectation, the hope, is that it will eventually converge to a stationary point of the flow. And stationary points of this flow are precisely the G2 structures for which the right-hand side of the flow equation is equal to 0. So are precisely the harmonic G2 structures, which on a compact manifold are precisely the torsion-free G2 structures. So this is the idea behind the flow, and the discussion before it shows you how to relate it to the fact that the closure of an initial closed G2 structure is preserved along the flow. So let's make some remarks on this flow, just to begin. So first of all, let's observe that the flow equation is not linear in phi. And this is because, again, for similar reason as in the case of torsion-free G2 structures, here you have the Hodge Laplacian, which has this expression here, and it depends on the metric induced by the tree form. And so this gives something that is nonlinear in phi. And since we require the G2 structure to stay closed along the flow, then of course we can rewrite the flow equation as we did at the beginning, so as d of d star t of phi t. And so this implies that the solution of the flow, if it exists, we shall say something about this later, must belong to the cohomology class of the initial point where it starts. So it must belong to the cohomology class of the closed G2 structure at time 0 that you are fixing on the manifold. Moreover, as I said already, on a compact manifold, the stationary points of the flow, namely those for which the right-hand side of the flow equation is 0, are given by torsion-free G2 structures. Since they are defined by the equation requiring the Laplacian of the three-fold to be 0, which on a compact manifold is equivalent to requiring that the three-fold is both closed and co-closed. And so one expects that if the solution exists for all times, then when the time goes to infinity, the solution should tend to a stationary point of the flow and thus to a torsion-free G2 structure. But let us also observe that if we restrict our attention to closed G2 structures, as we are doing here, then the stationary points of the flow are given by torsion-free G2 structures, even in the non-compact case. Let's write it in this way. And this follows from some computation that you can do involving the intrinsic torsion flow of the closed G2 structure that we introduced yesterday. And it goes as follows. So phi is closed, then this implies that if you take the differential of its Hodge dual, then it is equal to tau wedge phi, where tau was a notation for the intrinsic torsion form tau 2, belonging to the space, pointwise to the space lambda 214. So because of this fact, so recall that tau pointwise belongs to the G2 reducible submodule lambda 214, then this tells you that it is equal to minus the Hodge dual of tau by definition of that module. So if you take Hodge duals on both sides of this equality, you will obtain that minus the Hodge dual of the Hodge dual of phi is equal to tau, as squaring the Hodge dual on a 7-dimensional manifold gives you the identity. And this is precisely the codifferential of phi. So actually, another way of saying this is that the intrinsic torsion form tau is equal to the codifferential of the three-form defining the closed G2 structure. So in particular, as a consequence, you have the Laplacian, the Hodge Laplacian of the three-form phi that is closed and which is thus equal to d tau of phi is equal to the differential of tau. Since phi is closed. And moreover, of course, tau the differential of tau is now a 3-form on the manifold that you can compose according to the decomposition of 3 forms induced by the pointwise decomposition of the G2 module lambda 3 R7 star. So this tells you that you can write your d tau as some function times phi plus something like, let's say, the Hodge dual of some 1,4 wedge phi plus, let's call it gamma 27 plus a component inside here. And now what you can show with just simple computations is that actually you do not have this component here. So actually alpha has to be equal to 0. And this follows from the fact that d tau wedge phi is equal to 0. So you can try to do this as a computation. And whereas this function f here is equal to the squared module of tau over 7. So here you have something like the square module of tau over 7 times phi plus this component gamma 27. So what's going on here is that you have that the Laplacian of phi is equal to 0 if and only if, by definition, tau is closed, and this happens if and only if the square norm of tau over 7 times phi plus gamma 27 is equal to 0. But here we have a decomposition that is orthogonal with respect to the metric induced by phi. And so this is equivalent to saying both that the square norm of tau over 7 is 0 and that gamma 27 is 0. And so this tells you that tau has to be equal to 0. Namely, the 3 form is not only closed, but also co-closed. So this works for closed G2 structures also when you do not assume the manifold to be compact. So these are some first observations that you can make on the Laplacian flow. And maybe let me label it with LF if I will need to recall it later. So these are some first observations, and some other observations you can make regard how the objects that the 3-form phi induces evolve along the flow. And in particular, along the Laplacian flow, the volume 4 induced by the metric G phi evolves as follows. It is given by the square norm of tau over 3 times the volume of G phi t. Here, of course, recall that every quantity we will write in these equations will depend on the time. So this tau will be actually the intrinsic torsion flow of the G2 structure phi t, and the norm will be taken with respect to the metric G of phi t. So in particular, as you can see, this tells you that the volume 4 is pointwise non-decreasing along the flow, since this quantity is positive, or at least it's non-negative. Moreover, as for what concerns the evolution of the metric induced by the 3-form phi, well, this is equal to minus twice the Ricci tensor of the metric plus some quantity that is related to G. So we have the square norm of tau over 6 times G phi t. And again, here, tau always depends on the time. I won't repeat it. Plus 1 over 4, the map J phi t applied to the Hodge dual of tau h tau, where this map is the one we defined in the first lecture. So in particular, as you can see from here, the leading term of the evolution of the metric induced by a closed G2 structure along the Laplacian flow is precisely the equation of the Ricci flow. And in addition, you have some lower order terms, namely some derivatives that are or first or second order in the metric here. Sorry, first or zeroth order in the metric, as this one. So here you have some link also with the Ricci flow equation. What's more is that the Laplacian flow can be interpreted as the gradient flow of a suitable volume function on a manifold. And this was observed by Hitchin. And the result is the following. So we have that on a compact manifold, the Laplacian flow is the gradient flow of the volume functional defined as follows. So it goes from the space of G2 structures on the manifold to R and associates to a given G2 structure the volume of the manifold, which can be written as 1/7, the integral over m of phi wedge its Hodge dual, and it is equal to the integral over m of the volume flow induced by phi. And this is precisely because the norm of phi is the square norm of the three-form phi defining a G2 structure for the definition we gave is precisely equal to 7. But pay attention, this is the gradient flow of this volume functional restricted to the cohomology class of a given closed G2 structure you have. For instance, the given closed G2 structure you consider time 0, where your flow starts from, intersected, of course, with the space of G2 structures on the manifold. So you have this interpretation of the Laplacian flow as the gradient flow of a suitable functional. This functional is monotonically increasing along the flow and so in particular, if you have a solution of the Laplacian flow, then the volume of the manifold will increase as long as the time increases. And moreover, what we have is that a closed G2 structure is a critical point of the functional within a fixed cohomology class phi, if and only if it is torsion-free. So in other words, critical points of this functional are torsion-free G2 structures belonging to the cohomology class of the initial closed G2 structure you fixed. If, of course, any of such torsion-free G2 structures exist. And moreover, the critical points are of the volume functional on this cohomology class are strict local maxima of the functional modulo the action of the diffeomorphism. So this is a nice interpretation of the Laplacian flow that tells you that if you consider your flow and if the solution exists on a manifold, then as long as it exists, as long as time increases, the volume of the manifold will increase. And moreover, if there is any critical point of this functional, which is a torsion-free GT structure, then the idea is that the solution will tend to that critical point, of course, if any critical point exists. And we will see later that there are some examples when, for instance, you do not have, we have closed GT structures, but you do not have torsion-free GT structures where the flow does not converge. And we saw one example yesterday, and it will be precisely the example we will see. So the example by Fernandez on the two-stepney manifold. Let me say something about how to show the well-posedness of the flow. And then, of course, if you're interested in the details of this, of the proof of this result here, you can refer to the paper by Hitchin. Let me say something about the well-posedness of the flow, namely about the short time existence and uniqueness of the solution to the flow on a compact manifold, which is, of course, the first result one has to show if a flow that one is considering is a reasonable flow. So this result was proved, the short-time existence and uniqueness, by Bryant and Su. In a paper going back in 2011. And the idea is the following. So you have a flow whose flow equation is diffeomorphism invariant. So in some sense, it resembles the Ricci flow. And so in particular, you can try to apply the third type trick to simplify the flow equation. So the idea of the proof is the following. First, you apply the third trick to the flow equation. And so in particular, you consider the evolution. Let me omit the dependence on time for the various forms we have. So you will have TD star of phi plus the Lie derivative of phi with respect to a suitable vector field that depends in a suitable way on phi. And so this is equal to d star phi, and since phi is closed, applying Cartan formula, here you get plus the differential of the contraction of phi will be phi. And let me denote this operator here as some operator as E. So we have this operator E acting on phi. So you apply this trick for a suitable vector field V phi on the manifold. And you may refer to the paper by Bryant and Su to see the explicit expression. Now, what you do to understand whether the flow is well posed is, of course, this flow is non-linear, so you have to compute the linearization of the right-hand side of the flow equation and see whether this linearization gives you some elliptic operator applied to the first variation of the variation you are considering. And it turns out that this flow is parabolic, and so the linearization of this operator here is elliptic, only in the direction of closed forms. So this means that if you consider the linearization of this operator here at a given closed-GTSS structure with respect to some first variation, then you will get some second order, in general, you will get some second order operator in the variation, let's say psi, which is the variation of a family of GTSS structures depending on some parameter s when it is equal to 0, and assuming that this variation starts from a closed structure. So this is a second order operator in the variation that in general is non-elliptic. So if, in other words, if C is any variation, you can compute explicitly this linearization, and you will see that you won't get anything elliptic. But if you restrict to variations that are closed, so if you restrict to closed three forms as variations, so if you focus on variations along closed forms, then here you will get minus the Hodge Laplacian of the variation plus some lower order terms. And this now is an elliptic operator. And so this tells you that the first variation is elliptic in the direction of closed forms. So since it is not elliptic for any variation, there is no general theorem that you can apply directly here that ensures short-term existence and uniqueness of the solutions. And you have to apply the Nash-Moser inverse function theorem to get the thesis. So now the idea of this proof from Bryant and Su goes as follows. You apply the Nash-Moser inverse function theorem to get the thesis for the modified flow. And once you have the short-term existence and uniqueness of the solution for the modified flow, then you pull back the solution using a suitable diffeomorphism to get the solution of the Laplacian flow. So this is roughly how the things go. Of course, there is a lot of work to do to achieve this result. And here, let me remark that recently, Bedulli and Bezzoni noticed that it is also possible to apply a general theorem by Hamilton contained in his 1992 paper on the Ricci flow to prove the short-time existence and uniqueness for this modified flow directly. because some treatable hypotheses are satisfied by this flow equation, and so you get immediately the short-time existence and uniqueness of the solution for the modified flow using this theorem by Hamilton. So you can have a look to this very short note. It's, I think, around 4 pages. So what they proved is that short-time existence and uniqueness falls from a theorem by Hamilton. And this is because the flow equation that we wrote as dt of phi equal E applied to phi. So the modified flow equation we have here as a so-called integrability condition. Which is given by the differential from 3 forms to 4 forms. And this can be stated in first observing that if you take the differential of the phi, then it is 0. And then all the eigenvalues of the spectrum of the linearization of this operator here, restricted to the kernel of the spectrum of this operator here, have positive real part. So this is what an integrability condition is, plus, let's say, for the condition that I just say in words, and that you can find in the paper if you're interested. So in any case, you can show this result directly applying this theorem if you want. And moreover, of course, once you have short-time existence and uniqueness of the solutions, what you can do is investigating the analytic properties of the flow, understand what one can say about the long-time existence, understand what it is possible to say about the stability of stationary points, and all this about the analyticity of the flow, and all these results, all these properties, so all the analytic properties of the Laplacian flow were deeply investigated by Lotai and Bay in a series of 3 papers going back to 2015, around 2015, 2016, where they obtained long-time existence criteria that are based on the curvature and torsion estimates of the flow. They obtained backward uniqueness, real analyticity of the flow, and moreover, they also proved that the flow is dynamically stable along stationary points. So if your initial point is sufficiently close to a torsion-free G2 structure, then if any on the compact manifold exists, of course, then the solution of the flow will exist for all real time and converge to some torsion-free G2 structure in the diffeomorphism orbit of the torsion-free G2 structure you considered at the beginning. So many analytic properties of this flow are known. And as a further remark, as I already told you before, and as we saw last time, there are compact manifolds that admit closed G2 structures, but not torsion-free ones. And in particular, in such examples, of course, the flow may not converge. And this is precisely what's going on, for instance, in the example by Fernandez we saw in the third lecture. So we have compact manifolds admitting closed G2 structures, but no torsion-free ones. And so in particular, for instance, if you consider, for instance, the example by Fernandez, that recall it was a 7-dimensional manifold that we described yesterday, and that can be interpreted as a T4 bundle over T3, as it is a 2-step manifold. What we have is that if you consider the closed G2 structure we talked about yesterday, which in this case is the particular expression with respect to the basis of left invariant one forms, which is E123 plus E145 plus E167 plus E246 minus E257 minus E347 minus E356. So in this case, you can consider, so this is a closed G2 structure on N. In order to solve the Laplacian flow, so let's say dt of Pht equal Laplacian of T, dφt equals 0, and phi at time 0 equal to the closed G2 structure we have, it is usually useful to make some ansatz on the solution. And for instance, in this case, the idea is that you can look for solutions where you only rescale the coefficients of the summands giving you the threefold Bichelable functions and rewriting the flow equation as a system of ODEs for these functions that you put as coefficients. And if you are lucky, you will get some ODE system that can be solved. And this is precisely what's going on here. And in particular, with an ansatz of that type, what you get is that the solution to the flow starting at this closed G2 structure that we discussed yesterday is the following. So your Pht is equal to some function, let's say to the power of 3 times E123, and just the same part you already had for the expression of the 3-form phi. And of course, you are not always as lucky as in this case, because it may happen that some further summands appear in the solution. And so it is more involved to obtain a solution of the flow in those cases. Here, in particular, Ft is the following function. So you can just, starting from this, consider the metric induced by this threefold, compute its Hodge dual, and determine the expression of the intrinsic torsion form tau. And then at the end of the day, see that this equation here is equivalent to an ODE for this function here, that, by the way, has to be equal to 1 at time 0. And this function is 1 plus 10 over 3 t to the power of 1 over 5. And so in particular, the solution exists for t belonging to minus 3 over 10 plus infinity. And moreover, if you compute the metric induced by this threefold closed G2 structure here, you will obtain that Gφt is equal to Ft squared times the sum for I going from 1 to 3 of EI tensor EI plus 1 over Ft, the sum for I going from 4 to 7 of EI tensor EI. And so you have this kind of splitting of the metric that involves what's going on the base of your vibration and on the fiber of your vibration. And so in particular, in such a case, what's going on is that in some sense, the fibers will collapse as time goes to plus infinity. And in any case, you do not have the convergence of this closed G2 structure to any torsion-free one, as torsion-free G2 structures do not exist on the compact Lie manifold M for topological reasons, as we said yesterday. So of course, there are some cases where this approach may fail. And of course, as we saw in the second lecture, you have to consider manifolds, compact manifolds, whose topology is good enough in order to, let's say, have the hope that the manifold admits torsion-free G2 structures. So of course, there are still lots of open problems related to this flow, in particular, whether the flow exists as long as the torsion of the G2 structure is bounded. And for instance, whether we have examples that are compact and develop singularities at a finite time. Okay, so this is what I wanted to say about the Laplacian flow, which of course is not all what you can say, but you may have a look to the references I gave you if you're interested in seeing, for instance, the analytic properties of the flow. So for instance, the papers by IMBM and the paper by Bryant and Su, if you're interested in looking at the explicit and you are interested in looking in detail to the proof of the short-term existence and uniqueness of the flow. In the last part, I would like to tell you something about the solitons of the Laplacian flow, since they constitute a special family of closed G2 structures that have some something that you may think as similar as what you saw last week for solitons of the Ricci flow. So let's say something about the solitons of the Laplacian flow. And the definition for a Laplacian soliton is the following. So a Laplacian soliton of course, of the Laplacian flow is a closed G2 structure phi such that the Laplacian of phi is equal to some constant lambda times phi plus the Lie derivative of phi in the direction of some vector field. And in fact, these objects, which are special types of closed G2 structures satisfying this extra equation here, are in one-to-one correspondence to self-similar solutions of the Laplacian flow. So as it happens between Ricci solitons and self-similar solutions of the Ricci flow. In fact, if we let, let's say, rho t to be the function defined as 1 plus 2 over 3 lambda t to the power of 3 over 2, and so it is defined for 1 plus 2 over 3 lambda t greater than 0, you consider the vector field depending on time xt, which is given by rho t to the minus 2 over 3 times x where x is this vector field here now, and of course this lambda here is the same as here, and you consider Ft, a family of diffeomorphisms of the manifold that is generated by xt and is such that at time 0 it gives you the identity of the manifold. So if you consider these three objects and define phi t as rho t times the pullback of phi, where phi is a given closed-G structure, then what you have is that phi is a Laplacian soliton that satisfies the equation Laplacian of phi equal lambda phi plus the derivative of phi, if and only if phi t, as we just defined, so rho t pullback of phi with f, is a solution of the Laplacian flow starting at phi. And so this is again similar to what's going on for the Ricci flow. And in fact, also the proof is very similar, because if you consider this expression here and you take the time derivative of it, then you will get the derivative of rho times the pullback of phi plus rho t times the pullback of the derivative with respect to xt of phi. And so if phi t defined in this way is a solution of the Laplacian flow, then replacing this dt phi with the Laplacian and computing everything at time equal to 0, and assuming, of course, that phi 0 is equal to this phi, we get that the Laplacian of phi is equal to lambda phi plus the derivative of phi. And on the other hand, if phi is a Laplacian soliton, then it follows from a direct computation that dt of phi t, which has this expression here, and here we can now use all the definitions we gave before for rho, for x, and for f, then here you will get rho t to the power of 1/3 times the pullback with respect to f of lambda phi plus the derivative with respect to x now, so not xt anymore, for the way in which defined x here, compare this with the expression of rho, and with the fact that here you have rho to the power of 1/3 now. So by hypothesis, this is rho t to the 1/3, the pullback of the Laplacian of phi, because we are assuming that phi is a Laplacian soliton, but then this is rho t to the 1/3, the Laplacian of the pullback of phi done by f t, and then it follows from the behavior of the Hodge dual operator with respect to the scaling of the metric, that this quantity here is precisely equal to the Laplacian of phi t with respect to the metric it induces. And so in particular, if you have a Laplacian soliton, then the evolution equation of this family of three forms is precisely the evolution in the direction of the Laplacian. So it is precisely the Laplacian flow. So in particular, we have that Phi given by rho t pullback of a Laplacian soliton evolves self-similarly, and one has that also the metric will evolve in a similar way. In particular, you will have rho t to the power of 2/3 the pullback of the metric induced by the initial Laplacian soliton, and the volume induced by the self-similar solution is equal to rho t to 7/3 the pullback of the volume 4 of the treeform that is a Laplacian soliton. So we have these special types of closed-G2 structures that gives rise to self-similar solutions of the Laplacian flow that, similarly as in the case of the Ricci flow, are expected to play a role in the formation of singularities of the flow. And here, depending on the sign of the constant lambda, a Laplacian soliton is said to be expanding if lambda is positive, steady if lambda is 0, and shrinking if lambda is negative. And of course, as you may imagine, these definitions here come from the behavior of the volume of the self-similar solution along the flow. In particular, the volume will increase if the soliton is expanding. The volume will stay fixed if the soliton is steady, and the volume will shrink if the soliton is shrinking. So in particular, in the first case, Phi exists for t belonging to -3/2 lambda plus infinity, and so it is an immortal solution. In the second case, Phi exists for all real t's, and so you get an eternal solution of the flow. And finally, Phi, when it is shrinking, exists for t in an interval of -infinity -3/2 lambda. And so it gives you what is called an ancient solution. Okay. Now, similarly as in the case of the Ricci flow, when you have a compact manifold, not any type of a Laplacian soliton may occur. And in fact, we have this result that was proved with different techniques and different ways by Lin in 2013 and by Latai Wei in 2015, that tells you that actually on a compact manifold, a Laplacian soliton phi that is not torsion-free, so it's a closed-G2 structure which is not co-closed. Yeah, sorry, but I think that someone has the mic opened. Yeah. Okay, thank you. So if you have a Laplacian soliton that is not torsion-free, then it must solve the equation of the Laplacian soliton with lambda positive, so it must be expanding, and the derivative of phi in the direction of x, that has to be different from 0. So x cannot be neither 0 nor an infinitesimal automorphism of the G2 structure here. And the idea here is the following. So as I said before, and the volume of the compact manifold must increase along the flow. And so in particular, on M-compact, we have that the volume of the solution, where now this vol is the total volume of the compact manifold, is monotonically increasing. Along the flow. So this tells you that when you have a steady solitons on lambda is 0, we must have the derivative of the volume of the t has to be equal to 0. And so this implies, if you remember, that the volume flow evolves as the square norm of tau over 3 times the volume flow. This implies that tau t has to be equal to 0, and this implies that phi t has to be torsion-free, which is a contradiction if you assume that it is not torsion-free. And moreover, when lambda is less than 0, when it is negative, you immediately get a contradiction. Since the volume is monotonically increasing, and in this case, it should shrink, so it should decrease as long as the time goes on. So this explains why you only have expanding solitons on your compact manifold. Moreover, recall that the Laplacian of phi is equal to the differential of tau, which was equal to the square norm of tau over 7 times phi plus a component that belongs to the 27-dimensional submodule of the space of three forms. Thus, this implies that the Laplacian soliton condition, let me denote this by Ls, is equivalent to having the square norm of tau over 7 minus lambda times phi plus gamma 27 equal to the Lie derivative of phi with respect to x. And so, if this Lie derivative is 0, which means that either x is 0 or x is an infinitesimal automorphism of the G2 structure, then we must have that lambda is equal to the square norm of tau over 7 and that gamma 27 is equal to 0. Since again, these two summands here belong to orthogonal components of the space of three forms. So this tells you that you have something like the Laplacian of phi equal to lambda phi if the Lie derivative of phi is 0. And so this tells you that an equation of this form must have that lambda is greater than or equal to 0, since it has this expression here, and it is 0 if and only if phi is torsion-free. And moreover, you can show that on a compact manifold, an equation of the form Laplacian of phi equal lambda phi implies that phi is torsion-free. So in any case, you will, if the Lie derivative of phi is 0 in the expression of the Laplacian soliton, then in any case, on a compact manifold, you will obtain that actually the tree form is torsion-free. And in fact, the idea here is that in such a case, this is just the tau, and this is lambda phi, where lambda is this expression here. And what you can do is to compute 1/3, the zero differential of the cube of tau, and you will get minus the norm of tau to the power of 4/7 times the volume 4. And so similarly as in the case of Einstein matrix induced by Claudius structures that we saw yesterday, here you can take the integral over the manifold and apply Stokes to conclude that tau has to be equal to 0. So in particular, on a compact manifold, the only Laplacian solitons that one can have are the expanding ones, and moreover, you cannot have this summand equal to 0. So you cannot have neither x equal to 0 nor x an infinitesimal automorphism. But however, it is still an open problem to determine whether such type of solitons exist on compact 7 manifolds. So the open problem is the following: do Laplacian solitons, of course not torsion-free, as otherwise we know the answer, exist on compact 7 manifolds? So there is no compact example of this type so far.
Can I ask you something?
Yeah.
Can you show me the whole sentence, the statement of a proposition?
Yeah, this one here.
I missed some point. When you said that it's not torsion-free, then you mean it's only co-close?
No, so it's not torsion-free, so it means that it is different from 0. Sure.
Oh yeah. Okay.
Yeah, sorry.
Okay.
Yeah.
That makes sense.
So it does,
only close, right?
Only close and not torsion-free.
Yeah. Okay. Thank you.
Yeah, thank you. Okay, so we do not know whether there are compact examples, which of course must be expanding. And let me remark here that if lambda is different from 0, then the Laplacian soliton equation can be rewritten as follows. You can rewrite it as phi being equal to the differential of 1/λ tau minus the contraction of phi with x. And so in particular, if you have a Laplacian soliton that is either expanding or shrinking, so if lambda is not 0, then the tree form defining it must be exact. So you must have an exact closed G2 structure. And this is related, so this problem here is related to a more general open problem concerning the existence of closed G2 structures on compact 7 manifolds that are defined by an exact tree form. So the following are the compact 7 manifolds admitting closed G2 structures such that the tree form defining it is exact. We do not know the answer to this, and so in particular, this problem of the existence of Laplacian solitons on compact manifold is related to this more general problem. So we neither know whether exact G2 structures may exist on compact 7-dimensional manifolds. And for instance, a typical example should be the seventh sphere. So we do not know whether the seventh sphere admits closed G2 structures. And let me tell that in such a case, so for this more general problem, symmetry techniques are not useful. And this is because, as it was observed by Foda, I think last year, probably 2021, is that if phi is an exact G2 structure, so it is closed but in particular exact, then the Lie algebra of the automorphism group is trivial. So in particular, you only have a finite group of isometries acting on your compact manifold. And so symmetry techniques are not useful, and it is neither possible to obtain examples that are compact and locally homogeneous on quotients of simply connected Lie groups by lattices. And this was proved by Fino, Lucia Martin Marchand, and myself last year. So examples do not occur on the compact quotient of a simply connected Lie group by a compact discrete subgroup with the closed G2 structure that is invariant on them. So that is induced by a left invariant one on the Lie group G. So these are completely open problems. One is more specific related to solitons, one is more general related to exact G2 structures on compact manifolds, and if you want, on some specific compact manifolds. But in any case, to conclude, let me remark that more examples of Laplacian solitons of every type occur on non-compact manifolds. And there are many, many examples now. Let's say starting from 2015, there have been an increasing interest on this type of closed G2 structures. And there have been lots of developments so far. And we have many examples that have been obtained, for instance, on Lie groups. That were obtained by Laurette Nicolini, Anna Fino, and myself. And probably many other people. So this is, of course, an unexhausted list of results. And all of these examples are given by the so-called semi-algebraic solitons. So let's say of algebraic nature. As you have a Lie group G that is simply connected in 7-dimensional, you have a left invariant closed G2 structure on it, and it solves the Laplacian soliton equation with respect to a certain vector field on the manifold. That is induced by a derivation of the Lie algebra of G in a suitable way that I'm not going to explain, as I do not have so much time before concluding. But in any case, let me tell you that you have this type of expression, and examples are known where lambda is positive, 0 or negative, but none of these examples can descend to any compact quotient of the group by a compact discrete subgroup, because this vector field here is not left invariant. And so you will only have examples in the non-compact setting. So if you will get something, so this tree form, of course, will descend to any compact quotient of G, but it won't satisfy a Laplacian soliton equation anymore. Moreover, we also have many examples of, we have various examples of steady solitons on Lie groups that are provided by extremely rich pinched closed structures. And this was observed by Laurette and Nicolini, who also classified extremely rich pinched, who classified 7-dimensional Lie algebras admitting extremely rich pinched closed structures according to the definition we gave in the last lecture. And so what they proved is that examples of steady solitons on simply connected Lie groups are provided by left invariant, extremely rich pinch. Closed structures. And on the other hand, there exist examples of steady Laplacian solitons that are not extremely rich pinched closed structures. So you only have one of the two directions here. And to conclude, let me recall that we also have now some non-homogeneous examples of gradient type that are steady or shrinking. So with x equal to the gradient of some function f, so these are of gradient type, and that were recently obtained by Bow and Foda. And even more recently, so I think these papers go back to 2020, if you would like to have a look at them. And finally, recently, Askins and Nordstrom obtained complete shrinking and steady solitons of gradient type, which means that, again, the vector field is given by the gradient of some function, that are of homogeneity 1, on the spaces of anti-self-dual to forms on the fourth sphere, and the space of anti-self-duals to forms on the complex projective plane, which are, again, the two spaces considered by Bryant and Solomon, where they obtained the first examples of complete metrics with holonomy equal to G2. Okay, so I think that this is more or less what I wanted to tell you about today. Of course, there are lots of other interesting properties and distinguished classes, subclasses of the class of closed structures that can be investigated. Like, for instance, the extremely rich pinched ones I mentioned here and we defined last time, and I do not have time to talk about them, but let's say that we can conclude here. So thank you very much for your attention and for attending the whole course.
Thank you very much. Any question?
I have one more. When you mentioned about the reference of Hitchens before earlier today,
Which one,
can
sorry?
you give Hitchens?
Hitchens,
It's
yeah.
about the volume functional when you talk
Yeah.
about the earlier today. And can you give some more details about these references, like title or the year, so that I can look up?
Yeah, sure. Let me check in my laptop. Maybe I can give you also the archive identifier if I find it. Here it is. So it is, the title is the geometry of three forms in 6 and 7 dimensions. And it appeared on the archive in 2000.
Thank you.
Any other question? So thank you very much, Alberto.